zoning out, thinking about like, what am I going to do tonight? Thinking about plans for teal. Oh. Okay.
Today in Crosby's class, atoms. Everything in the world is made up of atoms.
That's the part that matters.
For
I'll leave the whole thing.
If you were to zoom in with a microscope, you would see billions of atoms. If you were to zoom in on one atom, you would see something similar to this. All atoms have a nucleus made of positively charged protons, neutrons with no charge, and then there are electrons, which have a negative charge, orbiting the nucleus. For right now, we're going to focus on the electrons. Electrons like to be in certain sublevels, of which there are 4, S, P, D, and F. A way to remember this is smart people don't forget. Each level holds a certain amount of electrons. S holds 2, P holds 6, D holds 10, and F holds 14. The quantum model of the atom explains this. The quantum model is set up on your basic y-axis, x-axis, and z-axis, which demonstrates the third dimension. The energy level 1 has a sublevel of S, which holds 2 electrons. The next level is 2. It has 2 sublevels. One is called 2s, which holds 2 electrons, and one is called 2p, which can hold 6 electrons, one in each half of these peanut-shaped orbitals.
See how it's building?
One way to know how electrons fill up these energy levels is by the diagonal rule. This shows the lowest energy levels in an atom. Each higher level...
So this diagonal rule you might find online or find in your book. We just read across the periodic table. You know, you go 1s, 2s, 2, or 1s, 2s, 2p, and so forth. You're reading straight from the rows of periods of the periodic table. This is another method. This is actually how I learned it. I had no idea how to do electron configurations until I started teaching. My teacher taught me this way, and I didn't understand it. But I think if you learned it now, this is just showing you the order of the orbitals and how they're filled, and they're going to show you how to draw the arrows through it. And that's just a technique for memorizing how to fill the orbitals.
Has one more sublevel than the previous. The red diagonal arrows show how the electrons fill the energy levels from the lowest to the highest. This is the reason it's called the diagonal rule.
So you'll see it's just like we say, 1s, 2s, 2p, 3s, 3p, 4s, 3d, remember that whole net n minus 1, 4p, and then that's actually 4d, 4p. 4d actually does come next because I don't know where 5 is. Oh, it's down here. She didn't finish it. She go 1 through 7 to build them, but that's a method, and we generally don't go really past the 4d sublevel anyhow.
How the electrons fill the energy levels from the lowest to the highest. This is the reason it's called the diagonal rule. To see this in action, let's work with an atom called magnesium. Magnesium has 12 electrons. Now remember the diagonal rule. 1s holds 2 electrons, 2s holds 2 as well, 2p holds 6 electrons, and the last 2 electrons fit perfectly in 3s. You can write these numerically. When you do that, you've got electron configuration. But we're not finished. For the final step, you look at the highest energy level. In this case, 3. From here, you take the electrons in the level. You could write some lengthy spiel if you really wanted to. Or you could just write valence electrons. These valence electrons are portrayed in the dot diagram. Let's do another example with...
Okay, so the dot diagram is the new thing, okay? Did you draw magnesium with 2 dots around it? And some of us may actually be familiar with this. Who's familiar with like a Lewis dot diagram? Maybe you drew them back in 7th grade, 8th grade? So this is something we're going to jump into next unit, but I want you to be familiar with it because everything connects, right? There's no, yeah, we go unit, but everything is cross unit. So everything is going to connect. The 2 valence electrons of magnesium, which were in the 3s orbital, are now depicted on a diagram like this. 2 electrons.
Let's do another example with chlorine. Chlorine has 17 electrons. Keep in mind the diagonal rule. Chlorine can be configured similar to magnesium. It's when we come to the final electrons we run into a difference. The p sublevel can hold up to 6 electrons. Even though there's only 5 electrons left to configure, they will still be distributed to the p sublevel. The outer level just isn't filled. Because of this,
how many valence electrons does chlorine have? 7. Who says 5? Great, nobody. 7, because there are 2 in the 3s and 5 in the 3p, so that's 7 total.
Chlorine isn't as stable as it could be. The valence electrons for chlorine are the combined electrons from the 3s and 3p orbitals, as they're both the highest level. The dot diagram for chlorine will look like this. Notice how it's missing 1 electron to be perfectly filled. To be stable and happy.
Guess what it's going to do, guys? How? Taking an electron from somebody else, which is how bonding happens. What charge would that give chlorine if it gains an electron? Remember, the electrons are negative, that will give it a -1 charge, and that's how we get the ions that we've been depicting with the little charges at the top. Okay, let's finish this.
Happy, chlorine wants to fill this slot. Let's say magnesium drifts close to chlorine. Since magnesium has 2 valence electrons that it's willing to give up, chlorine will attempt to steal one. Like a lasso, chlorine will pull at one of magnesium's valence electrons. Though it puts up some struggle, chlorine will gain the valence electron it wants. Now chlorine is stable, but magnesium still has 1 valence electron it doesn't need. Another chlorine will come along and, through the same process, gain magnesium's last unwanted valence electron.
Woo.
Now all 3 atoms are stable and happy. Magnesium, since it lost negatively charged electrons, is a positive ion. Both of the chlorine atoms, since they gained electrons, are now negative ions. Since opposites attract, magnesium bonds with the 2 chlorines in a process called ionic bonding. The result is, drumroll please,
Magnesium chloride.
an ionic compound called magnesium chloride.
Okay.
We can shorten magnesium.
Okay, so this whole process, I'm just trying to put it in perspective. Why are we talking about these electrons? Why are we talking about the valence electrons specifically? Because they are later important in charges, which allow us to then find the compound formula, compound name, and really talk about the chemistry behind the actions. So, all right, that's all for now. I want you guys to practice. This is a practice open to the partner quiz. I was going to give this quiz to you guys today, but I thought we'd practice first. We'll do somebody, let's take less than 8 minutes. Here our table, and I'll go over it. You need to have some confidence in what you're doing, okay? So the first example is vanadium. The symbol is V. It's atomic number 23. If you do not know what you're doing, please, please, please ask questions. I will not know unless you tell me. Sure. You can do it. No, I want to go over this. This is the personal quiz. So I want you to do this on your own. Do this in your warm up, because as I go over it, you'll grade it, and then that will give you something to study later on. Okay, white one. Make it so that stand there with me. I'll scroll down in just a minute. If you want to do it independently, totally fine. But need some help. And use a clean periodic table with no cheat sheets, not the one with the SPs. Try to use something that would be fresh, like you given on a test or something like that. No cheat sheets. Okay. I'll guarantee you it'll be helpful if you write out the electron configuration first. And then
Yeah.
All right, are you done with number one? Okay, I'm gonna scroll down so you can see number two. Raise your hand if you are 90% done. Okay. Where are we at on number two? Are we stuck or are we still working? Still working. Okay. Let's take one more minute.
Like if you have a 9
All right, guys, 30 seconds here or less. Try. All right, lovelies, let's do this. Grab a separate color pen or let somebody else check. I want you to be honest with yourself so that you know where you stand. This is a personal, reflective exercise. If you still don't have any idea what's going on, please ask us out, okay? So, I'm quickly going over this. Ready? Vanadium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 3, because it's 3 electrons into the d block, right? That's the electron configuration. Sorry, orbital diagram. You guys, I think I saw most of you guys doing it right. The only part I think you would have had an issue with is at the very end. You write 4s2, up and down, arrows up and down, 3d, so 1, 2, 3, 4, 5 orbitals still, despite how many we need. They're all labeled 3d. And then electrons go in one at a time with the same spin, one up, up, up. Those are 3 electrons. Great. So we should be okay with the orbital diagram. Empty orbitals, how many are there? 1, 2, good. There are 2 empty ones, 100% empty, okay? Because the second, or part C, says how many are unpaired. Well, that's what these 3 are showing, they're unpaired. So there are 3 unpaired electrons in the d orbitals. How many valence electrons does vanadium have? Quick recap, valence electrons are the very outside energy level. What is the last energy level? 4, the 4th energy level, because that is that 3D that appears is actually an energy level within it. It's a lower, it's a higher energy, but it's a lower energy level. So we're going to stick with the theme that valence is the 4th energy shell, which gives us 2 valence electrons. Okay, so we should be okay there. In terms of the charge that vanadium would form, what do you guys think? To me, octet. To me, it's you know, magical number. How many electrons could it lose? 2, its valence electrons. It very well, just because it can, okay, transition metals are variable. They have variable transition states, they have variable charges. It possibly could lose these 3 as well. Okay, so I would accept either just vanadium 2+, meaning it lost those 2 electrons, or vanadium, how many are these? 5. So it very well could form a 5+ charge. It generally doesn't want to, it probably couldn't gain, because it would have to gain 1, 2, 3, 4, 5, 6, 7. It would have to say gain 7 electrons to get all that all the way filled. But vanadium 2+ is our best answer. But there are some variability, because transition metals are just weird. They kind of don't follow normal trends all the time. But oxygen does. It's crystal clear. There is one answer for this one. So orbital diagram, the one where, for this one, I'm actually going to draw it real this time. 1s2, 2s2, 2p. So you have 3 orbitals. How many are here? How many? 4 electrons, because oxygen is the 4th one over p block. 1, 1, 1. So one's roll and up 1 right there. So there are 2 empty or 2 unfilled ones. How many electrons does oxygen need to gain to have a full subshell? 2, and I'm going to draw that in green here. 1, 2. So 2 electrons. Okay, so what would the charge be of this oxygen? Oh, what? Hold on. Say it out loud, loud and proud. Oh, 2 minus. That's kind of how we say it. 2 minus or -2, whatever you say. That is the ion, oxygen 2 minus. Because it gained 2 electrons, so that gives it a 2 negative charge, because there are negatives occurring more often now. So the oxygen ion would then have the same electron configuration as who? Who? Neon. Because it is closer. It's now, instead of being 2p4, it will be ending in 2p6, which is what neon ends in. So the electron configuration is stable now because it has the electron configuration of a noble gas. Okay. Who got, let's say 85 or plus? You can guesstimate that. Okay. I'm feeling good about this. Yes, ma'am. That B, you talking about that B? It's saying in question B right here. So the oxygen. That may have been confusing. Sorry. Okay. All right. So we have 2 things. Yeah, we have enough time. The periodic trends that we started yesterday. We're going to quickly go over them. But you read about them a little bit in your Reading Guide 6. So I'm going over the reasonings behind them, not necessarily what they are. Because the what they are part is, I think, pretty obvious in how the name is phrased, the phrasing of the name. Then we'll get to, I hope, to our flame test lab, one of my favorite labs. So you can probably figure it out. It deals with. Okay. So let's kind of see where we are. The more active you are with me, the most likely we will get there. Okay. So take additional notes either on the back of,
Brian, you can either take a, you can take on the back of your periodic table that you have your SPD and F on, and you can draw on this and make it a big active periodic table, unless you are secret, sir. And then you can take it on the back of your periodic table. Whatever you gotta do, keep your periodic and stuff together. We did start this yesterday.
so the two factors we talked about extensively, okay, for like 5 minutes yesterday, were ZEF. F is ZEFF. That's nuclear effective charge. ZEF is how we say it in abbreviated form. Because Z is the Z number. Z number, just giving you some background here. Z number is the atomic number. And Z number is also the proton number. So that's what we're really talking about, is the number of protons. So that is why we call it the effectiveness of the protons, the effectiveness of the nucleus. Okay, one thing we did talk about yesterday was that these things were bigger down here on this end of the periodic table, and they were smaller here. And that was because when you went down a group, so let's go down a group. So I'm starting on the shielding effect one. Does it say across a group? It doesn't. Okay, so remember the shielding effect was the group trend. And this shielding effect related to what? You wrote this down yesterday. Shout it out loud and proud. Whenever you're ready. Alina, what you got?
Electrons and atoms are blocked from
Okay, so electrons in the outermost levels are blocked by the internal electrons, the core electrons. But what is it related to? You guys told me okay, backtrack. Why the heck does this thing get bigger as you go down the group? What are you adding as you go down the group? Energy levels, okay? Simply, there are lots and lots of energy levels as you get down. There are a few energy levels up top. So the reason it's bigger because of these energy levels, you know, we're growing in size here, okay? So that's going to be the main reason why something is bigger. That's just radius, though, okay? And because there are because we are going, actually I have this on the next slide, that's why I don't really want this here. Because we're going down, that's why it's getting bigger, right? But as we go across the period, this way, what's happening to the size? As we go from left to right, what's happening to the size? It's actually getting smaller. You saw this yesterday on your chart. You saw that lithium was big and neon was smaller. So the small ones are over here, okay? Remember, atomic radius trend, the increasing trend, trends so that it's increasing to the left, not to the right. Okay, the reason why, though, this is the part that is probably more important. Whenever you're going to let's go from lithium to neon, what's different about their protons? How many protons are in lithium? Look at your periodic table. 3 protons. Okay, how many in neon? 10. So between those, who has a greater effective nuclear charge? Who has a stronger pull on their electrons? Neon. Why? Simply it has more protons. So if you have more protons and you're in the same energy level, your size is not different because of the energy level, because you're in the same energy level. It's different for another reason, and that's because this one has a stronger pull, greater nuclear charge, greater ZEF, however you want to phrase it. So it's small, and lithium doesn't have a great attraction for its electrons, so it's big, and it's over here. Okay, so that's the reason. And what I would phrase this as is ZEF increases from left to right. And if you know what that means, then that should suffice. ZEF, the effective nuclear charge, increases as you go from left to right. And the reasoning for that, why does it increase, guys? Because the atomic what? The atomic number increases, but what is that actually describing? Atomic number, protons, okay. ZEF is increasing from left to right because protons increase. And if protons are increasing, what is that doing to the size of the atom? Getting smaller because it's very attractive. So ZEF is increasing from left to right because protons increase and attract electrons. Therefore, it's getting smaller. Kind of a one-sentence deal there. Narrowed it down. Okay, so that's how the atomic radius differs. Across the period, it's getting bigger this way because there's less Zeph on the left side, and it's getting bigger down the group because there are more energy levels. That's it for atomic radius. So we have one more part of atomic radius, and that's what I just explained here. And it's the ions. So ions that we just talked about, gaining electrons and losing electrons, they're related. So ionic size is related. This is the same general trend. But we actually have to figure out why a cation and an anion are differently sized than the parent that they came from, so from the actual atom they came from. So let's go with lithium versus lithium ion. Lithium forms a 1+ ion. That is called a cation. Positively charged. So what I'll tell you is that cations are actually smaller than their parents. Atomic radius is smaller. And I'll say than parent, and you'll know that means than the atom that it came from. So for example, lithium is going to be big, and lithium ion is going to be smaller. The reason why is because once you lose electrons, the battle is lost. The protons win, people, and they suck in the remaining electrons. They attract them because they overpower them, which causes the shell to decrease in size, just because of the more attractive nature of the protons. So there's more protons to pull in the available electrons that are left over. So can you give me what you think about anions? The opposite, right? They're larger. And so don't forget, anions are negatively charged particles. What was the anion in the example from the video? Which was the anion in the example from the video? Chlorine, right. So magnesium was our cation in that video, so it formed a plus charge. So we have chlorine versus chlorine ion, and it's a 1- charge. So what we have here is we have a kind of a normal sized parent, and then this guy, when you add an electron, we actually have electron repulsion. So what happens when two things repel? They do what? They spread apart. What do you think that does to the shell, the cloud, where the electrons exist? Makes it bigger, right? So if that's just kind of a natural, kind of common sense deal there. The same thing happens, right? When an anion forms, it gets bigger because of the electron-electron repulsion. So the atomic radius is larger. Thumbs up when you got this one. This is one thing you may not have read a ton about. Okay, we did atomic radius and ionic radius. What do you think the next one is here? Or maybe some of the other trends you remember reading about? Electronegativity, ionization energy, and electron affinity. Okay, those are the last three. And they're very closely related because they all trend the same direction. So let's talk about kind of what they are and then how they trend. Okay, ionization energy, IE, for the next one. And you're going to want to become very comfortable with one of these. I like to tell you what's on your test. On your test on the back side, you're going to have to explain one of the trends of your choice. You'll explain what it is, how it trends on a period, and how it trends on a group, and why. Okay? So it's like 4 sentences. And you can draw pictures to help you, but you'll have to pick your favorite and then stick with it. So make sure you make a note of that on your notes. Okay, so ionization energy, it's a form of energy, right? It's in the title. And it's the energy to make an ion, because it's ionization energy. So if we're talking about making an ion, sometimes we make cations, sometimes we make anions. In this case, we are wanting to make a cation. So it's actually the energy that you require to rip an electron off of an atom. So to take it, to make it now positively charged. What does VE mean? Valence electron. Okay. So the energy needed to take an electron to make a cation. Who is more likely to form a cation? Who wants to lose electrons? Which side of the periodic table? Why the left? Right, so these have 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8 valence electrons. Okay, remember the goal is to get to 8. So these guys are like, hey, I only got to lose 1. Let's lose this. Let's get out of here. We're going to have 8 electrons after that because they actually back up to be like that of a noble gas. These only have 2 electrons to lose. Not a big deal. These have 7. Ain't no way they're going to lose 7. They'd rather gain 1. That's a different story. Okay, so these like 1, 2, and 3 valence electrons, they want to lose electrons. So if you want to lose electrons, you're not going to put up a fight for that. You'd actually really like to do that. So that's why, and I'm going to show you on this finger method here. That's why over here in the corner, on the left side of the periodic table, it's a very low amount of energy to lose an electron. They want to. But over here, they're like putting up a fight because there's a lot of energy that's required to do that, which is not very favorable. So I'll show you it like, well, I'll actually just change the direction of this arrow. How about that? So the energy is increasing, and that's increasing. So as you go from left to right on the periodic table, you are increasing in energy. And that's because, guess what's high over here, guys? What's high on the right side of the periodic table is one of our factors we talked about at the very beginning. Those are only 2 factors. Not atomic radius actually is a trend. So yesterday's notes is what I'm talking about. Were the 2 factors. We already talked about, so Alina gonna give us the explanation on one of them, which was which was shielding effect. The other one is effective nuclear charge ZEF, right? Okay, so on the right-hand side of the periodic table, ZEF is high. We have a large amount of protons. We have a large attraction. And that's really the reason why the ionization energy is also high. Because if you have a high attraction, you love your electrons. You don't want to release them. So don't you think it's going to be hard to get them? It's going to be hard to rip off the electrons? Just because the protons are so attractive. So the high ZEF, or the high effective nuclear charge, makes a high attraction, which relates to increasing ionization energy because there's a high attraction for your electrons. Over here on the left side of the periodic table, there's less protons, there's less ZEF. They don't care about their electrons as much. It's really easy to get them. And then, so we talked about the period. This is a period trend. And then down the group, the increasing energy is higher. So the ionization energy is higher up here, lower down here. Why? What's different about the size here? Give me the size up top. Small or big? Small, right? So we have atomic radius, small on the top, large on the bottom. So if I have an atom that's this big here, and an atom that's this big here, and there's our proton, and there's my electron. Which electron is easier to get? This one or this one? Because it's farther away. And so it's like just plucking them off left and right. So the bigger the atom, the less attraction to its outside shell, just because they're so far away. That's why the energy is higher up here, because those are close, and they're like, dude, it's mine, don't take it, because it's so close. Okay, so that's kind of how this trend works in terms of ionization energy. Pretty much the same for electron affinity. The definition is different. Okay? Do you guys know what affinity? Affinity means? Anybody? Okay, some people in this class have a high affinity for, I have a high affinity for chocolate and dogs, my husband. What are those affinity? Attraction, love, okay? So electron affinity means you love some electrons, okay? You really, really, really desire electrons. So if you love electrons, then sometimes once you get them, you become a stabler, happy person. So when I get chocolate and caffeine, I'm a stabler, happy person most of the time. So whenever we're making an atom take on an extra electron, we're making it an anion. So this is kind of the opposite definition of what we just talked about. So it's energy to add an electron to make that negatively charged ion. So this one's similar. Whenever you give an electron to NM, so a non-metal, do they want that electron or do they not want it? You tell me, because remember the nonmetals are kind of over here. Do they want it? Yes or no? Yeah, they're like, yes, please give me the electron, because that means I get octet, remember? Okay, because they're going to gain an extra electron to look like a noble gas. So giving an electron to a nonmetal makes it more stable. And when you are stable, are you like really on a caffeine high and really energetic and crazy? Or are you kind of chilling? Chilling, okay? So that's basically what the what the atom's doing. If it's more stable, it actually has to do something to make itself more stable. It's going to release energy. And that's why the energy increases again to the right, because everything over here is going to release energy when they get an electron because they like it. They want the electron, so they're going to give off the extra energy, which actually makes them more stable, which is a good thing. Okay? Being stable is a very good thing for an atom. But everything over here doesn't necessarily release a lot of energy, which giving an electron does not make it more stable. This is the harder of them, because this definition is a little bit more in depth. And then going down a group, small atom, big atom. If you are, I'm going to draw this the other way again. If you are trying to add energy, add the electron to something that's small, it actually has a higher amount of energy release because it's got the attractive nature of the protons and electrons, so it's like lots going on. There's a lot of energy released. If you're adding something out here and the protons are really, very far away from it, that has there's lesser amounts of energy released because it doesn't even know the electrons existed. First of all, the proton's way inside, the electrons are way outside, and there's less effect on it just because it's a bigger atom. So this one most people don't choose to explain, just because this one makes some sense. But I don't want to give you everything because then your head will explode and we'll have you. Okay, so there's more to it, but that's an advanced level. Okay, last one. What is it? Ionization energy, electron affinity, electronegativity. This one we will use a lot in the next unit. Trust me. You want some practice with this one. So these are the big four here. Okay, so electronegativity. This one doesn't really tell you a lot about what's going on, except for something with an electron. But the negativity issue is its want for an electron in a shared situation. A shared situation is a covalent bond. And that covalent bond just means that usually two nonmetals have gotten together, and both of them want an electron. So instead of maybe one taking it and one giving it, they're just like, hey, we'll hold it in the middle, we'll both touch it, let's just pretend we have it, but we're sharing it. And that's what a covalent bond is. We're going to get to that in our next unit. But sometimes there are two different elements, and one of them wants the electron more in that shared situation. So think of it as a greedy kid who doesn't share very well. Like they have to share, but they're going to have it 5 days out of the 7 days of the weekend. Preschool or something. Okay, so it's just something that's more greedy, wants the electron more, simply because it has a high electronegativity. So again, the electronegativity trend is up, So it's higher energy or electronegativity at the top of the group and a high electronegativity over at the right. And the reasoning relates to what we've talked about with ZEF and the shielding effect or the size. As you go to the right on the periodic table, what happens to ZEF? What happens to ZEF? It gets bigger. ZEF increases from left to right. Okay. Increasing effective nuclear charge means that you have a great attraction for your outside electrons. Not only your outside electrons, but if there's any in the near vicinity, guess what you're probably going to do? Take it, right? And this one it's going to share. It's going to share. It's going to kind of take it more often. So increasing ZEF from left to right makes them more electronegative, which means to, I'm going to say take, but it just means to overshare, so take more often, an electron from an outside source, so like another atom, for example. And so that's why there's such high electronegativity for everything over here on the right. Going down the column, down the group, large, small. Okay, remember, who's doing the attraction for the electron? Who's literally attracting the electrons? The nucleus, right? If the nucleus is really far away, like it is here, do you think it's going to be able to attract that electron that's out there? Not very much, because it's just so far away. It doesn't even know it doesn't even know its own electrons exist, much less another person's. So that's why these electronegativity values are low on the bottom of the group, because the nucleus is so far away. There's a lot of shielding going on, and it doesn't know that there's an electron out there to attract. This little guy is like, hey, there's an electron out there. Attract it. It's close. Let's just take it in. Keep it warm. Okay? And so that one is so far, has such a short distance, there's basically no shielding at the top, and that lack of shielding means that there's a very good attractive force. So the electronegativity is high, has a good attraction. And that's going to, in the end, relate to the octet rule and trying to get everybody octet and so forth. Okay? Okay, now that I've bored you to tears, we have two choices. We have practice that relates to problem set 6, which you're starting tonight. It's going to have it due tomorrow. Ignore the program. We start your homework. We have 30 minutes left. Or we can try to knock out the plain test lab. And then we'll do some more practice tomorrow in class. Option 1. Option 2. Option 1. Option 2. Majority rules. Okay. We will practice tomorrow in class. You're starting PS without me, but we will have it due maybe at the end of class tomorrow after we practice them together. Let's go ahead. Like 6 each side. Plain test lab. Okay, let me show you how this is done real fast. And we'll practice this more tomorrow. That means we're going to spread this out. This should not take us more than 30 minutes. I have to demonstrate to you how we do it. But basically what we are doing is we are going to take a little wire. We're going to take a wire, we're going to dip it in a solution, and we're going to catch it on fire. And we're going to observe it and make conclusions about what the heck is happening to the solution, okay? Benium lab groups, still, I'm going to turn the gas on. You guys get your goggles on, get the lab out of the notebook. I mean, don't get it out, leave it in the book, open the book. And I'm going to turn the gas on, okay? Get the Bunsen set up. You should know how to set up a Bunsen at this point. You're a pro. Go. I have no Wednesdays. I have meetings. Okay. You like me?
Okay, but all the planes have clouds. If you're to draw them while you're having it, probably like 10. On the back, okay. I gave you a half sheet so we could actually do this a little bit faster. Let me just see how this works. With my goggles on, you guys read the pre-lab real fast by yourselves. Read the pre-lab. You're writing your purpose down. Like 10 seconds. Alright, 5, 6, 7, 8, 9, 10. Okay. Everybody leave your room. I'm going to show you how to do this so you're efficient. This is a nitrogen wire loop. It might be slightly contaminated because it is plain. Every solution has a one attached to it. Do not replace this nitrogen wire loop. I've cleaned most of them so that they'll be the correct color. This is copper. So look on your paper, you see Cu2 plus or CuCl2. It says copper. It actually says it says barium underneath it. That should be copper. You see on your little data sheet? It says barium. That's big out loud. That's copper. Okay. There are 2 spaces on the bottom of the data sheet that give you extra space for other solutions you may have available to you. All you do is now some of these little nitrogen wires that are little because I had to hand make them just for you. This one's a nice one. It's big. My hands are always in place. There's a little loop on the end. You dip it into your solution. You get a little bit on it. You can actually see it looks like it's a little bubble with it. And then you put it into the inside blue cone on the side of it. And it looks like this. You're like, oh, I didn't see that very well. Let me do it again. Don't touch your hand. Okay, so then what you're going to do is write on the color of that plane. These are all knowns. Knowns mean you have the name is copper, and now you have the color of it, blue. At the end, I'll give you unknowns, which is going to identify them based on your observations of the first one. Now, you only have about 5 to 6 of these at your table. Other groups might have other ones. You can kind of rotate to the tool right next to you, but I tried to really space it out, okay? So get that Bunsen burner on and get started. Okay, if it's a yellow flame, there's too much oxygen. Too little oxygen. Girls, you've got too much gas in the out. Way too much gas.
So I guess we can start with this one.
Oh, note to self, listen. Note to self, if you hold the nitro wire there too long, it will start to burn and turn a yellow color, which is not necessarily the color you see. It can. Some of them are yellow.
I didn't get to see it.
Alright, you guys should be rotating to other stations too, but do not mix up anything.
No, we don't.
Hey guys, look over here, guys. So make sure you're waiting for her. So the best way to do it is not leave it in there for God knows how long. Dip it and then wave it through like the edge of the intercom. It's easier to just dip it in and out and then dip it again. You can go using that just over and over. Yeah. You can see like that. There you go. You can go to the last station, rotate as you need to. Yeah.
No, I think we okay. Okay.
So make sure she takes that little stick off. Yeah. So guys, go check on your station. All right, take 2 more minutes on identifying as many knowns as you can. Strontium, ST, or sorry, SR. We borrow your space. I'm putting 2 unknowns in your desk. There are many
Oh, yeah, sorry. Thank you.
Okay, listen. Everybody should be identifying unknowns. I'm going to give you guys 8 minutes to identify as many unknowns. Now, you've got to be confident, okay? So if you're not sure, then don't try to identify it. You must identify correctly 3 of them. Pressure's on, people. There are unknowns at all locations. You must successfully identify 3 of them. You get the others as long as you're doing your future. So, we actually we're done with our I don't think I can I know. You guys have unknowns that you're done with this? Hey, when you're done with that,
This one we got. Pretty good one.